Hi, this is Pratik Verma.
And this is Siddharth Prince.
So this is our attempt to predict annual income using census dataset. So our objective was to create a grammatical evolution model which can solve the classification problem to predict whether the person represented in the dataset has an income greater than 50,000 per annum or not. So the dataset we had was the smaller version of the real dataset of census income dataset, and yes, we had to publish our scores over the leaderboard of Kaggle. We tried so hard, but we weren't able to get into top three.
At least for the public results. Fingers crossed for the private results, but yeah, we tried. So, moving on to the grammar definition. We based our grammar on the example of the heart disease problem. And as we can see, we've used the same kind of logical operations and conditional branches and Boolean feature definitions. But a small addition here is that we added the if codon so that we give a little bit more flexibility in terms of conditional branching. And other than this, we obviously had to change the number of Boolean and non-Boolean features that we have here because we needed to fit it according to the dataset that we were using and not the heart disease dataset. So that goes without saying. But you can also see that there are a lot more Boolean features here because we've gone with the one hot encoding, which we will see down the line. Other than this, we did try multiple runs using other variations like NAND and NOR logical operators, but we found that it didn't have much of an effect, so we ended up dropping those. Now with pre-processing, we had gone with label encoding at first, where we wanted to keep the same number of features, but just encoding the labels according to the numbers. But after that, we did give one hot encoding a go based on the demo video for the for the heart disease demo given by Connor in his video, and we found that this worked out way better. So we've gone with this. And of course, one hot encoding, as discussed before, increase the dimensionality of the dataset. But yeah, that's what we've gone with. Next up, we've done some normalization. Initially, we did the minimum and maximum. That is, we followed how Connor did it in the video, where we used the minimum and maximum of each feature, and we subtracted and divided by the difference between the max and min values for each feature, so that we can get a consistent range for each feature, which the model might find easier to find correlations for. But then taking cues from our other module, that is Introduction to Machine Learning, shout out to Kieran, we tried going with standard scaling, and we did find a little bit of a marginal increase or increase in performance with respect to our final prediction. Other than this, we tried out other ideas, but it didn't work out so well.
So we tried dropping capital gain and loss features as these two columns are having very high number of zeros. So in order to handle the missing data, we tried simple imputation and KNN imputation. So for most sophisticated imputation using k nearest neighbors, which was attempted, but this technique leverages the value of neighboring instances to impute the missing values. So we tried using these techniques to get the proper value for missing values.
Yeah, but it didn't really work out. That is also because there are so many consecutive zeros in the data for these two features. We really didn't know what to do. We tried dropping those entire features as well, but yeah, that actually ended up performing worse, even though there's very few actual data entries with actual values in this. So we ended up not being able to solve this problem.
So the best setup we got with the population size of 1000 and maximum generation we did was 150 with crossover of zero point 0.7 and mutation of 0.02, and we did achieve the accuracy of around 76.64% for this 78.64% for this particular setup. But we tried different setups. We tried to change the population size to, we went to till 1500 with the population size, maximum generation to 200. We tried to change the tournament size to 8, 4, 5, 6, and we also tried to change the codon composition to eager, but as compared to the lazy one, eager was showing worse as than the previous one, so we didn't choose the eager one. We try to mess with the codon size, which is initially 255, but we try to increase it, decrease it, but overall we got the good answer with 225 only.
We also tried changing the max wraps, where we thought if for smaller tree sizes or smaller depths for the tree, if it could wrap more than once, it might give some positive values, but that also ended up not doing much.
So our setup continued. We tried with simple reputation. I mean, we tried to replacing the values with median, but as there were so many zeros in between the data, it wasn't, I think, making much sense. We tried with elite size, as we know that we cannot increase the elite size more than the Hall of Fame size. So we were trying like elite, putting elite size 2 with 4 Hall of Fame size. So in this particular setup, we got the score of around 77.64%. But still, the first setup was the best setup we got so far.
So finally, coming over to our results and observations, so as we've seen before, some of the pre-processing that we've done have had some positive effects. Like when the very first time when we ran these without any sort of pre-processing, like scaling, or not doing one hot encoding and going with label encoding, we had our Kaggle predictions around 75 to 76%. But then after these, it did work. But as we saw, a lot of it didn't work. Maybe our approaches were not right. Further exploration is warranted for these. And also, a big observation that we've made here is that usually when it comes to training models, we have a split where there's a lot more training data than the testing data. But for in this particular instance, it's been like half of the training data. There's only been half of the data available for testing that has been allowed to be used for training. So we found this very odd, and this could be why that we weren't able to consistently increase our scores as we would have hoped.
So in our conclusion, what I thought that messing with the models and playing with the values parameters gonna make much difference, but my experience is like if you are putting more time in data pre-processing, cleaning and everything, it's gonna put more effect to the end result. We tried different feature engineering. There are like we just tried one hot encoding and label encoder, but there are way too much encodings which we can try, and the better argument, we can eliminate these features where the entries of zero were way too much, such as the capital gain one and the capital loss one. and it does require way too much of hyperparameter tuning. So it's a probabilistic way to get the proper score. So yes, that's
Yeah, so maybe augmenting those zero entries in a better way could help, but this would require further experimentation, and obviously more parameter tuning and experimentation with that could be warranted. So yeah, that's our attempt, and thank you.
thank you.
Thank you.